Good morning, everyone. I'm Dr. S.K. Singh, and I'm delighted to welcome you all today. Today's presentation is titled Cleanroom Classifications, with a focus on grades A, B, C, and D. We'll be exploring what these classifications mean, their significance, and how they impact our work. So, let's get started and dive into this important topic. Good Manufacturing Practice, or GMP, guidelines for pharmaceutical cleanrooms are essential to ensure that the products we produce are safe, pure, and effective. These guidelines are carefully designed to minimize the risk of contamination from particles, microorganisms, and pyrogens during critical sterile processes like preparation, filling, and packaging. GMP cleanroom requirements are quite comprehensive. They cover everything from how the facility is designed and maintained to how personnel behave, gown, and perform cleaning procedures. One important aspect is the cleanroom classification system, which helps us define how clean a space needs to be based on airborne particles and microbial control. There are two major standards that form the foundation of these classifications. The first is ISO 14644-1, which categorizes cleanrooms from ISO Class 5 to ISO Class 9, based solely on airborne particle counts. The second is EU GMP Annex 1, which applies similar principles but also incorporates microbial limits, gowning expectations, and operational states, such as at rest and in operation. Together, these standards help us maintain the strict cleanliness levels required for pharmaceutical manufacturing and ensure consistent product quality and safety. Now, let's look at how GMP cleanrooms are classified into 4 different grades: Grade A, B, C, and D, based on the criticality of the operations taking place inside each one. These grades are aligned with ISO classes, which helps us have a standardized way to measure particle limits across different environments. Starting with Grade A, this is the most critical area, where the most sensitive operations happen, such as aseptic filling, compounding, and handling sterile products openly. In these zones, the environment must meet the ISO Class 5 standard, both when the room is at rest and during operation. That means the particle count must be kept at or below 3,520 particles of 0.5 micrometers or larger per cubic meter. Moving to Grade B, these areas serve as the background environment for Grade A zones and support aseptic processing without direct product contact. For Grade B, the ISO classification is also ISO Class 5 when at rest, but during operation, it needs to meet ISO Class 7 standards. Particle limits are a bit more relaxed here. At rest, up to 3,520 particles per cubic meter, and in operation, up to 352,000 particles. Understanding these classifications is crucial because they ensure we maintain the appropriate environment for each stage of production, minimizing contamination risks and maintaining product integrity. Let's take a closer look at Grade C and Grade D cleanrooms, which are essential parts of our sterile manufacturing process. Grade C cleanrooms are used for less critical tasks, such as preparing solutions and handling components before sterilization. They have specific standards for particle counts, with a limit of no more than 352,000 particles that are 0.5 micrometers or larger per cubic meter of air. In terms of international standards, Grade C cleanrooms typically correspond to ISO Class 7 when at rest, meaning the air cleanliness is quite controlled, but slightly less stringent during operation, which is classified as ISO Class 8. Moving on to Grade D cleanrooms, these are designated for the least critical stages of sterile drug production. This includes tasks like initial handling and washing of components, where the risk of contamination is lower but still needs to be managed carefully. For Grade D, the particle limit is much higher, up to 3,520,000 particles of 0.5 micrometers or larger per cubic meter. They generally align with ISO Class 8 both when at rest and during operation, reflecting a slightly relaxed control compared to higher-grade cleanrooms. Understanding these classifications helps us ensure the right environment for each stage of production, maintaining product quality and compliance with GMP standards. Let's talk about cleanroom classifications and what they really mean. These classifications are based on the maximum allowable concentration of airborne particles, specifically those that are 0.5 micrometers and 5 micrometers or larger. Essentially, the cleaner the room, the fewer particles you can find floating around. Regulatory guidance, like Annex 1 and ISO 14644-1, sets out the standards for these classifications. They require not only defining the class of cleanliness, but also routine monitoring to ensure ongoing compliance. These standards cover grades A through C conditions, which are typical in many controlled environments. Now, when we get to grade D, things are a little different. Only the limits for when the room is at rest, meaning no one is actively working inside, are predefined. For the in-operation state, where the room is actively being used, manufacturers need to set their own limits based on a thorough risk assessment. This approach allows some flexibility, but it also emphasizes the importance of understanding the specific risks involved in your cleanroom activities. Remember, maintaining proper classification and monitoring is crucial to ensuring product quality and safety in these sensitive environments. Let's talk about the at-rest state, which is essentially our baseline for cleanliness. This state represents a moment where everything is ready but no active manufacturing is happening. All utilities, including the crucial heating, ventilation, and air conditioning systems, are installed and fully operational at this point. Equipment is carefully arranged, but importantly, it hasn't been set into motion yet, and there are no personnel inside the room. This setup helps us establish a clear baseline for cleanliness, giving us a snapshot of the environment's inherent purity, free from human activity or equipment operation. Now, when we consider cleanroom classification, the at-rest state has specific particle limits. These limits define how many particles of certain sizes can be present, ensuring the environment stays within strict cleanliness standards. Understanding this baseline is key, because it helps us compare how the environment behaves during active operation, and it sets the foundation for maintaining the integrity of our cleanroom environment throughout the manufacturing process. Now let's take a look at the in-operation state, which really captures the real-world dynamics of a cleanroom. Unlike the at-rest state, where everything is quiet and controlled, the in-operation state is lively and active. HVAC systems aren't just turned on, they're fully engaged, maintaining optimal conditions. Equipment hums in its designated mode, and the cleanroom is bustling with personnel actively working. This is the environment where manufacturing actually happens, so it reflects the true challenges of maintaining cleanliness amid human activity and machinery. Understanding this state helps us appreciate the importance of cleanroom classification, especially when it comes to particle limits. During operations, particle counts can fluctuate, which is why we set specific limits for what's acceptable. These limits are crucial. They ensure that even with maximum activity, the environment remains within the required cleanliness standards. So, in essence, the in-operation state is about managing real-world conditions, balancing the activity levels with strict cleanliness requirements to keep everything running smoothly and safely. While non-viable particle counts are indeed central to classifying cleanrooms under ISO 14644-1, it's equally important to consider viable or microbial contamination control, especially in pharmaceutical GMP environments. Cleanrooms must be monitored for microbial contamination using validated sampling methods, and these results are then compared against established microbiological limits, which are outlined in EU GMP Annex 1. Now, these limits are defined by the number of colony-forming units, or CFUs, permitted in different sample types across various cleanroom grades. Think of CFUs as a way to quantify how many microbes are present. These limits aren't just numbers. They serve as critical alert or action thresholds within our environmental monitoring programs. They help us evaluate whether the cleanroom environment is within acceptable limits during initial qualification and ongoing routine monitoring. In essence, maintaining microbial limits is vital for ensuring product safety and compliance, reinforcing the overall integrity of the cleanroom environment. Let's take a closer look at microbial contamination limits and how they relate to clean room classifications. These limits are crucial because they define the maximum allowable number of microorganisms in the environment, ensuring product safety and quality. Different clean room classifications are established based on these microbial limits, with stricter standards for more sensitive products. For example, in ISO classifications, a Class 5 clean room has a very low level of microbial contamination, which is essential for pharmaceutical manufacturing or biotech processes. Understanding these limits helps us design and maintain environments that minimize contamination risks effectively. This connection between contamination limits and clean room classification is fundamental to our overall goal of ensuring sterile and safe production environments. Now, let's discuss some of the key methods used in environmental monitoring programs to detect and track microbial contamination in air and on surfaces. First, we have active air sampling. This method involves pulling a specific volume of air across a nutrient medium, like an agar strip. The idea is to capture and grow any microorganisms present in that air sample, allowing us to quantify the airborne microbes in terms of colony-forming units per cubic meter, or CFU per cubic meter. Active air sampling is required in grade A and B cleanroom areas, where the highest levels of control are necessary, and it is also recommended in grades C and D to ensure ongoing quality assurance. Next, we have passive air sampling, often called settle plates. This method uses Petri dishes with growth media that are exposed to the cleanroom air for about 2 to 4 hours. During this time, particles in the air settle onto the plates by gravity. This approach is particularly useful for detecting larger particles and assessing the risk of surface contamination. It provides a different perspective compared to active sampling, especially in terms of assessing potential contamination that might settle onto surfaces or equipment. Both of these methods are vital tools within our GMP cleanroom monitoring programs, helping us maintain the stringent environmental controls necessary in pharmaceutical and biotech manufacturing. By combining active and passive sampling, we can get a comprehensive picture of microbial presence in the environment, ensuring we stay compliant and safe. Now let's look at surface monitoring, which typically involves contact plates and swabs. Contact plates are pressed directly against surfaces like walls or equipment to check for any microbial residues that might be present. This helps us determine if cleaning has been effective or if there's a potential risk of transferring viable microbes. Swab samples, on the other hand, are especially useful in hard-to-reach areas or on irregular surfaces where contact plates might not be practical. Both methods are essential tools for assessing cleanliness and ensuring that our environment remains within controlled microbial limits. Moving on to personnel monitoring, this involves using contact plates to sample areas like fingers, gowns, or sleeves. It's a way to evaluate the risk that operators might introduce microbes into the cleanroom environment. This is particularly important in grade A and B areas, where the highest levels of cleanliness are required. Overall, these viable monitoring methods, whether for surfaces or personnel, are crucial for maintaining the integrity of GMP cleanrooms and ensuring product safety. They allow us to identify potential issues early and verify that our cleaning and gowning procedures are effective. When it comes to selecting sampling locations, it's really a careful process that's driven by a thorough risk assessment. We look at several key factors to help us make the best decision. First, the room classification plays a crucial role. Different areas in the cleanroom are designated based on their cleanliness levels, and this directly influences how often and where we perform microbial sampling. Next, we consider airflow visualization studies. These studies give us valuable insights into how air moves within the space, helping us identify spots where microbial contamination might be more likely to settle or spread. It's about understanding the environment from a dynamic perspective, not just static conditions. And finally, our process and operations knowledge is essential. Having a deep understanding of how the manufacturing process works and which operations are critical allows us to pinpoint the areas most at risk for microbial contamination. Putting it all together, these factors guide us in choosing sampling locations that truly reflect the areas of highest risk, ensuring our monitoring is both effective and efficient. This meticulous approach helps us maintain the integrity of the cleanroom environment and supports overall quality and safety. When it comes to risk assessment integration, it's crucial that our sampling plan isn't just a standalone activity, but is actually woven into a comprehensive risk assessment framework. This means we need to identify areas of higher risk and make sure those receive more thorough scrutiny. By doing this, we focus our resources where they are needed most, helping us better control potential contamination sources. Moving on to real-time monitoring, this is a step beyond periodic sampling. Implementing real-time microbial monitoring systems allows us to get continuous insights into the cleanliness status of the cleanroom. This ongoing data helps us catch issues early, rather than waiting for scheduled samples, which is vital for maintaining a high level of control. And finally, prompt corrective actions are essential. If we detect deviations from microbial limits, we need to act immediately. Quick response not only prevents potential contamination spread, but also reinforces a proactive approach. It's about staying ahead of problems rather than reacting after they happen. All of these considerations, integrating risk assessment, real-time monitoring, and quick corrective actions, are interconnected. They help us create a robust sampling strategy that supports overall quality and safety in our cleanroom environment. Now, let's discuss some typical operations that are performed within Grade A cleanrooms. These usually take place under ISO Class 5 conditions, often using laminar flow units, and are situated within a Grade B background. The key activities include replenishing sterile bulk materials, containers, or closures, staging sterile primary packaging components, and assembling sterile connections for single-use systems. Common use cases for these environments are critical, including aseptic filling of sterile products, aseptic compounding and mixing, and loading or unloading sterilizers like autoclaves or lyophilizers. Moving on to Grade A cleanroom applications, these are the highest level of contamination control. They are used for the most critical aseptic operations. These zones require unidirectional airflow, such as laminar airflow cabinets or isolators, and are usually maintained under positive pressure with strict limits on particulates and microbes. Each GMP cleanroom grade, from A through D, is designed with specific manufacturing activities in mind, depending on how critical the process is and the potential risk of contamination. Understanding the appropriate use of these grades is essential to stay compliant with regulations like Annex 1, and ultimately, to ensure the safety and integrity of pharmaceutical products. Now, let's talk about Grade B environments and their role as the background for Grade A zones. These areas are crucial because they support aseptic manufacturing processes by maintaining the necessary sterility levels. Essentially, they help prevent contaminants from entering during material and personnel transfers, which is vital for ensuring product quality. You'll often see Grade B areas used for preparing and staging materials that will go into Grade A processing. They also include gowning rooms right next to the aseptic core areas, which helps control contamination as staff prepare to enter the most critical zones. Additionally, these areas facilitate the transfer of sterile equipment into Grade A zones, ensuring everything remains sterile during movement. Another key application is the cleaning and sanitization of tools used in aseptic filling. Keeping tools sterile is non-negotiable. And finally, they are used for assembling sterile filtration systems before use, which is essential for maintaining the integrity of the sterile environment. It's also important to note that Grade B areas are typically maintained at ISO Class 5 when at rest, meaning they have very strict particulate controls, and ISO Class 7 during operation, allowing for some increase in particulates but still maintaining high cleanliness standards. All these applications highlight how Grade B environments serve as a critical foundation, supporting the sterile conditions required for successful aseptic manufacturing. Now, let's talk about Grade C cleanrooms and their role in manufacturing. These cleanrooms support less critical but still controlled steps in the process. They're suitable for operations where the product or components are exposed before sterilization, or when preparing solutions and intermediates. Some common uses include weighing and dissolving raw materials, preparing bulk solutions that will later be sterilized, filling products that will undergo terminal sterilization, and assembling components for later sterilization. It's important to remember that these cleanrooms are maintained at ISO Class 7 when at rest, but they operate at ISO Class 8 during use. Monitoring is still essential to ensure cleanliness and control, but it's less frequent compared to higher-grade cleanrooms. Overall, Grade C cleanrooms play a vital role in supporting manufacturing steps that require controlled environments, helping to maintain product quality while allowing for efficient production processes. Grade D environments are primarily designed for basic cleanroom control, which is usually needed during initial or final processing steps after sterilization. While these zones don't require the same level of cleanliness as higher-grade areas, they still play a crucial role in reducing contamination in the surrounding spaces. Key activities in Grade D cleanrooms include washing and drying equipment and components, as well as the initial unpacking and inspection of raw materials. These processes help ensure that everything entering the more sterile environments is as clean as possible. Another important activity is the final assembly of closed systems before sterilization, which minimizes exposure to contaminants. Reusable tools are cleaned and stored here, ready for future use. Additionally, sterile connectors are assembled under closed conditions to maintain their integrity and sterility. It's also important to note that Grade D zones are equivalent to ISO Class 8 standards. They often serve as entry points into higher-grade areas, acting as a controlled gateway to more critical environments. Overall, while Grade D cleanrooms are less stringent than higher grades, they are vital for maintaining the overall cleanliness and integrity of the manufacturing process. For further support, please don't hesitate to reach out to us. We're here to help you with any questions or additional assistance you might need. Remember, our goal is to ensure you feel confident and well-equipped moving forward. Thank you so much for your time and attention today.